Welcome in my video explaining how my 6502 based breadboard computer is working. If you'd like to see this computer in action, check other videos. This video will be explaining only how it was built and why I made the decisions to build it like that and not in the other way. So that's my primary setup. This is how it is built. And originally I was using an 6502 design from Ben Eater, which you can find on this sheet. So this is what I started with, and basically most of the elements that you are seeing here was implemented. Later on I have to add or change some things because simply things were not working as I expected, and that was actually the fun that was with this project, because you can imagine that the troubleshooting or trying to find out why something is not working was the most exciting part of the project. So I will start with explaining the elements of my setup, comparing to the original design and what elements are not existing in my project and why. So if we will look at the original scheme, so there are two on the Ben Eater webpage. However, this is the most complex. The following elements I'm having on my computer. So starting from the main processor, which is Western Digital 65CO2, which is located over here. I have exactly the same processor. I will call it later on 6502. Then I have the ROM and RAM chips. So this is my ROM, this is my RAM. ROM is installed in the socket so that I can pull it out and use it to program. Then I have the VIA chip, so it's also Western Digital 65C22 chip. So the VIA is used in the original Ben Eater computer to interface with the outside world, and this is exactly how I'm using this as well. So the VIA chip is located over here. And then we have SIA chip. In this design, it's W65 C51. However, I'm using the Rockwell version of that chip, but basically the functionality of that it's the same. So those chips are the chips that I'm having as well. On top of that, there is a clock signal generator. So this is my generator, which is 1 megahertz. The reset circuit, which is located over here in my example. Then a few logic chips to control the bus and decode the addresses to make sure that during accessing different areas of the memory, the processor is accessing RAM, ROM, or external chips, depending what we need to address. And this is this chip over here. So most of the elements that was in the original scheme are also in my computer. The things that haven't been implemented or have been later removed are the MAX chip that is using that in this design is used to convert the logic levels from TTL levels to the RS232 levels, and simply I do not have that part in my computer. Instead of that, the two lines which are used to transmit the data, the RX data and TX data, in my system they are connected directly to the USB TTL to serial converter. I do not need to have other chips connected, and the benefit of that is that I can just plug the USB cable and connect that directly to my computer. So that's the first design difference. The second design difference is that originally I also had the display connected to my computer. However, I wanted to have something more modern, and instead of using the LCD display, I wanted to have the proper video output, and my concept was to build a VGA output to this homebred computer. So to do the VGA output, I experimented with different options, and I didn't want to have anything too much complicated at the first stage, and I decided to use the Raspberry Pi Pico. This is the Pico 2040 version, which is quite capable of generating VGA signal as an output for my computer. However, the Pico is 3.3 volts compatible, so to make it running with my computer, there are two voltage level converters that are 8 bits, and there are 2 of them because I'm using in total 9 lines to make sure that my data will be properly output. This is connected to the VIA chip, so Raspberry Pi is not connected directly to the CPU address bar. It's connected through the VIA output port B to the address space of the computer. So instead of having this LCD display in my setup, I have those 2. Actually, I have this one logic level converter plus in additional the second one, which is transmitting one more control line, and those control lines are then hooked up into the Raspberry Pico, and this is using few output lines to generate the video output, and this video output is then transmitted using the VGA socket into my computer. The next element, which is not visible on that scheme, is the keyboard interface. So the keyboard interface is built on some scheme that I found also over the internet. You can find a schematic how to build, or the information how to build the keyboard interface, also in one of the Ben Eater's video. This schematic here was made by a person that had issues with original scheme, and therefore there are some additional elements added to the original design. However, in my design it was working without those original elements. So basically, to make the keyboard interface running, there are few approaches that can be used in this schematic and also in one of the Ben Eater video. The concept was that the data from the keyboard interface are sent to shift registers, and then once the complete scan code is transmitted into the computer, the circuit here is informing CPU that the data are ready to be read out from the port, and the whole 8 bits is read at once from the shift registers. So in my scheme, I do have this part of the circuit. So I have a capacitor, I have a resistor, and a diode. They are located here. There is connection through the 7414 NAND gate, and another gate here, which is going into this element here. What I do not have in that interface, I do not have this, and I do not have this, and I do not have those elements here. They are not needed. Basically, the keyboard interface is running quite nicely with the build that is basing on the Ben Eater's original scheme. On this scheme, you can also see the display, which is not in my setup, so this is not existing. The other and the last difference from the original schemes are connected with the way how the clock signal is generated for the ICEA chip. So in this and in many other schematics that I found over internet, and unfortunately with those that simply was not running for me. This is built in a way so that into the 2 pins of the ICEA chip there is a resistor and a quartz resonator connected with the capacitor to the ground. Unfortunately, that setup was not working for me. I was playing with the different values, and sometimes I was able to make it run, sometimes not. And to make it more reliable, it looks that what we need to do, instead of using that, the best way would be to use the clock signal generator, like it is used for the main clock signal. So we could just have the same generator, but instead of 1 megahertz, we could have 1.8432 megahertz connected directly to the XLT1 output. So if we would connect this here and connect here to the ground and connect here to the plus 5 volt, we would get a stable clock signal that will make this chip running all the time, every time when it will starts. So this randomness effect will not longer be applied. However, I didn't had that, so I did differently. And because on my 74H14 I have few gates still left, I made a following. So I used the chip. I used two gates of the chip and make a signal generator for me that was working like that. So here I connected the crystal with a resistor, and then the legs were connected to the ground. Then the output was connected to the input of the next gate, and the output of the next gate was connected here, and that make me a stable clock working for the ACR chip. So the complete circuit for that you can see here. So there is a resistor, oscillator, plus two capacitors connected to the ground, and the output is connected to the next gate, and this output from the next gate is connected as an input for the clock signal for the iShia. And basically this is working. Now the other element, as I mentioned, was the VGA output. So the way how I wanted to build that is the way that I make it as simple as possible. And the concept was that if every time when I will write something to the port B of the VIA chip, it should be displayed on the screen. And for that, I wanted to make the system simple as possible, as I mentioned. So I found out in the VIA documentation chip, when I was reading the schematics, how the communication with the external world can be done. And there was an interesting statement here about so-called plus mode, which is later on called in the documentation pulse mode, and actually I think that the pulse mode is the way how it should be called, which basically is doing this what I wanted to do. So whenever we will write anything to the port, the system or the VIA can make a pulse on the CA or CB2 pin, and it basically will not wait until any answer, it just pulse. This can be achieved by setting up the proper bits in the CA or CB control register, and this is exactly this what I was looking. So the pulse output, if you will set up in the CB2 control, it will make the system to generate a pulse every time when you will write anything to the port. So in my setup, every write operation to the port B is triggering this pulse. The system basically do not have any feedback. I mean, there is a way to configure the chip to wait for the feedback, so that from the system point of view or the CPU point of view, we will know when the external system will receive the data and will confirm that the data have been received. In this setup, basically, we just inform the outside world that the data have been written to the port, and we do not care what will happen with the data. So this is in my setup, it's designed in this way. So as I mentioned, there is 8-bit lines connected to the port B of the VIA chips, and this is going through the shift level register, and then it is going out to the Raspberry Pi Pico. And I have also one line hooked up into the CB2 port, and this one line is actually this what is triggering the pulse mode, and it is also connected to the Raspberry Pi input. And from the Raspberry Pi, it is done in that way. So there is a ERQ setup on the edge of this line here. And whenever it goes from low to high, the system is reading the complete 8-bit from the port, and then it's stored in the circular memory, and later on it's processed in the main loop. So basically the system here, or the Raspberry Pi, is acting as a dumb terminal that is processing the data, displaying them on the screen, and it's also it's having a support for some ANSI terminal codes, so that I can clear screen, change the color, set the cursor positions, and so on and so on. That is everything on the high level, how the things are built in my system. And if you are interested to understand or see more, just let me know.